Hello and welcome to 7.5, modeling data using logarithmic functions, or, if you want to call it logarithmic regressions. We're going to start off with our PlanetCalc.com website to do the function approximation and regression analysis. In this example, I'm doing the one that's on the first page of 7.5, the population of Canada. And so we see population data points that are in the thousands. So this is 34,000. So we're going to assume that this is actually 34 million people, 34,278,000 and change. And the Y values here that we've included based on what the paper says. So again, you should probably have the paper in front of you. It says the years since 1870. So back down here where we have 1, this is 1871. This is 1 year since 1870. This is 1881. So it's 11 years since 1870. And so we type our numbers in with spaces in between, not commas. Be really careful here that you don't by accident put a space to reflect how it shows on the worksheet. I know that there's a space there instead of a comma, but we want to keep all of our numbers tight and let the space indicate to the computer that you're starting a new data point. And again, you can turn off all of the functions here, make sure your exponential regression's turned off, and now we're focusing on the logarithmic regression. The decimal points, if you want them all, you can go up to 20, you can have a little bit less if you need, but why not have them up at 20 if we can? So we'll calculate, and it creates a scatter plot for us. Again, the idea is that all these blue dots are the data points, and it's drawing a yellow line that's the closest possible fit to all those data points. So you can see that some fall off of it, but some are like really close to it. And so the fit, or how good does this line fit, is shown here with the correlation coefficient, and we can see it's 0.9963. That's fantastic. You can feel really confident that this is a function that models that data, and that you can probably use it to make predictions in the future. So as usual, I like to copy the function of best fit. The thing about copying this guy here is that we've got a couple changes that we need to make once we move it into the metacalculator. So the graphing calculator of metacalculator. The first things first is that when we paste it in, it comes in with the strange kind of symbol that you need to replace the first negative sign with like the negative off of your keyboard. It's a different kind of character that they use on PlanetCalc, so we need to undo that and just put in a normal minus sign here. And the second thing that we need to do on metacalculator is to put brackets around the x. So actually, let's just double check that. Do we even need that? I kind of checked that before. Oh, all right, great. So yeah, like I said, just brackets around the x. Everything else will be fine. It's just that funny negative sign out front. And so we can see our graph is in the form of a logarithmic function. As we're going from left to right, we're meeting the function first in quadrant 4. So we meet it first in quadrant 4 as we're moving from left to right, and then we leave it in quadrant 1. So going from quadrant 4 to quadrant 1, that's one of the end behaviors of a logarithmic function, and this is an example of the increasing logarithmic function. As x gets bigger, y gets bigger. So on our question is asking us about the year when the population of Canada is going to go past 20 million people. So I think part of it is remembering that the table is in thousands. So it's not that we need a table of 20 million people. We need it to start at 20,000, which is the same as 20 million. So if we ask it to start at 20,000 with an interval of 1 and we press enter, we'll get our x value of 20,000, and the y value is 101.8. Now, 101.8 sounds like a really funny year, but it's 101.8 years since 1870. So 101.8 years, it's 102 years after 1870, or basically in 1972. So in 1972, we'd be looking at the population of Canada going over 20 million. So if you, and that's if you're given X and you want Y. If you are given Y and you want X, so if you know your Y value, you have to use your intersection. Add that as an equation and go to intersection. It's not a question that's on here, but it's often things that we have to look for. So just be careful. Tables used for the X when you know X and you want Y. Intersections used for Y when you want X. So just a little word of sort of understanding here is that this ln, this is an L and an N. It's not a 1, it's not an I. The ln is a special form of log. We know pi is sort of a reserved variable. There's another variable like that called E, and E is the natural number. 2.718 something, and it's also it never ends, so that's the natural number. If you have a log, now the normal log on your calculator is log to the base 10 when you push that log button. If you have a log to the base E, we give it a special number, and that's ln. So this ln x is still representing log. I know this is supposed to be logarithmic regressions and we're dealing with ln, but this is a special kind of log. It's a log to the base e. So just be careful if you're ever typing this yourself, that's an L, not an I, and not a 1.